Welcome back. In this video, we're going to look at example 3 in section 8.4 of our workbook. In example 3, this gives us another opportunity to practice using that alternating series theorem. All right, so we're asked in part A to prove that this given series converges. So first, let's determine that this is in fact an alternating series. So we could rewrite this as the sum of n equals 1 to infinity of -1 to the n minus 1 times 1 over 2 n cubed minus 1. So we see as n goes from 1 to infinity, that this term here is always positive. So even when n equals 1, we have 2 minus 1, which is positive 1, so 1 over 1, positive. Okay, so that means we can conclude that we are alternating. We can say, yes, alternating series with what is Bn? B sub n is 1 over 2n cubed minus 1. So now let's start a little bit more scratch work. So we know that we're alternating, but we need to check those two conditions in order to determine convergence and use that alternating series theorem. So part A, we need to consider the limit as n goes to infinity of our B sub n's. So for us, that would be 1 over 2n cubed minus 1. And now we see as n goes to infinity, this term in the denominator goes to infinity, which means that whole denominator goes to infinity. So 1 over infinity is in fact 0. So check, we have the first condition met. Now let's consider condition B, or the second condition. So that is, we're going to look at that n plus 1 term. So in our case, that would be 2 times n plus 1 cubed minus 1. And we need to compare that with the nth term in our series, or with the bnth term. So that would be 1 over 2n cubed minus 1. So now we need to compare these two terms and ask, well, which one is bigger? And can we say which one's bigger in general? So one thing we can notice here is that how do these denominators compare? Well, n plus 1 is bigger than n. So that also means n plus 1 cubed is bigger than n cubed. And n is an integer, so if we were in the case where we had like n plus 1 was a fraction, then that wouldn't be true. But n is an integer, a whole number. So when we cube it, it's going to be bigger than if we just started with n. So that whole 2 times n plus 1 cubed is bigger than 2n cubed. So then if we subtract 1, we're still going to get a bigger denominator in the first term. So with a bigger denominator, that means that the fraction itself is smaller. Consider dividing one pizza amongst more people. Then each slice a person gets is smaller than if you have less people at your party. So we do have inequality in this direction, which is the condition that we need to meet for the alternating series theorem. So we are good to go. We have an alternating series. We have the two conditions in that theorem met to prove or to claim that our series converges. Very cool. So now let's write this up in a proof. So we can say that since the limit, and maybe instead we can want to just make sure that we know that we have an alternating series. Since the series given is alternating, since the series given is an alternating series, and we have that the limit as n goes to infinity of 1 over 2n cubed minus 1 equals 0. And finally, we also have 1 over 2n plus 1 cubed minus 1 is less than or equal to 1 over 2n cubed minus 1 for all n. That means the given series converges by the alternating series test. Awesome. So there's our proof. And we can always double check that we've included everything. Have we written our proof in a complete sentence? Have we included the conditions of the theorem? We have alternating, we have the limit going to 0, we have inequality. Have we stated the theorem we're using? Yes. Do we have our conclusion? Yes. All right, awesome work. Okay, so now let's continue this example by looking at part B. So in part B, we're asked to estimate the value of this convergent series that we just showed was convergent, accurate to within 0.005 of its true value. So let's think about how we get started on that. So recall that alternating series estimation theorem says that the error between our actual converging value and the nth term in the approximation, or the nth partial sum, is going to be less than or equal to bn plus 1, the nth plus 1 term. So what does that mean in English? That means if we use n terms to approximate the sum, meaning so use s is about s sub n, then the error will be no larger than b sub n plus 1. So again, that error can be computed by subtracting the actual value or by subtracting our partial sum from the actual value. Okay, so we need to determine, well, what partial sum are we going to use? Well, we want that error, s minus s sub n, to be less than or equal to 0.005. But we know that that error is going to be less than b sub n plus 1. So we need that b sub n plus 1 to be less than 0.005 to guarantee that our error is less than that desired value. We're going to just make a box around that because that's what we're getting at here. We want to know, well, what n do we need to use in order for the nth plus 1 term to be less than 0.005 to ensure that our error is less than 0.005. So what we can do is set up this inequality here that we've made and then solve for n. So let's go ahead and do that together. So the bn plus 1 term looks like 1 over 2 times n plus 1 cubed minus 1. We want that to be less than or equal to 0.005. So let's go ahead and work with this inequality to solve for n. Okay, so what does this mean? Well, what we can do is multiply both sides by that denominator here, because we're going to solve for n. We want to isolate n on one side of this inequality symbol. So that looks like 1 is less than or equal to 0.005 times 2n plus 1 cubed minus 1. So now let's go ahead and distribute that 0.005 into each term on that right side. So that means we have 1 less than or equal to, so 0.005 times 2, we can get out our calculator or think about that for a moment. It's going to be 0.01. So we have 0.01 times n plus 1 cubed. Oh, I hope you caught me here. This should be a cube, not a square. And then so now we bring that 0.005 into negative 1. We just have negative 0.005. So now what I can do is I can add that 0.005 to both sides to cancel it out on the right side. So now we get 1.005 is less than or equal to 0.01 times n plus 1 cubed. And so now I can divide both sides, because again, wanting to isolate n, so we can divide both sides by that 0.01 to get some things on that right-hand side to cancel to help us be able to isolate. So what do we get after we do that? We can continue down here on a new page. So now we have doing this calculation here. You can get out your calculator to follow along. but we should be getting 100.5 as less than or equal to n plus 1 cubed. So now we can take the cube root of both sides. I'll use a different color here so you can see the operation. So that cubed root will cancel out that cubing. And we can see then that we have cube root of 100.5 is less than or equal to n plus 1. So now all we need to do is subtract 1 from both sides. So therefore, we have cube root of 100.5 minus 1 is less than or equal to n. So what does that mean? So let's get out our calculator and compute what this value means as a decimal. So this value is about 3.649. So we need 3.649 to be less than or equal to n. That means that n needs to be bigger than 3.649. So that's what we've just concluded. So so we can kind of chase back and just kind of reflect why we just did this. So if n is bigger than 3.649, then we get all these same inequalities that we could chase back up. And then in the end, we would be able to have that our bn plus 1 term is less than 0.005. The bn plus 1 term is going to be bigger than our error. So that means our error would also be less than 0.005. So what should we have for n? Well, n needs to be bigger than 3.649. So you could use any n larger than that you wanted. The larger the n, the more accurate you're going to be. But the first n we could just choose is 4. We could say if n equals 4, then this inequality is satisfied. So let's go ahead and work out the rest of this example then. So to summarize, we can get an approximation of the sum if we use n equals 4 terms. So we're thinking about the sum from n equals 1 to infinity of -1 to the n minus 1 over 2 n cubed minus 1. So this is going to be about s of 4, which is 1 minus, so I'm going to have to write out those first 4 terms. You can go ahead and check me on this. Actually, I encourage you to pause the video and write this out for yourself. And then once you have a solution, you can compare your work. But so we write out that sum. Using our calculator, we approximate the sum of these 4 terms to be 0.9443. So here, using S of 4, this approximation is accurate to within 0.005 of the actual sum, or of the actual value of our series. And again, just if we want to think through why that is, well, s minus s sub 4 is going to be less than or equal to b sub 5. We saw that b sub 5, or in other words, 4 plus 1, is going to be less than or equal to 0.005. So our error is also less than 0.005. Awesome. All right, great work on this example.